Okie doke. We have more people. We have more people. Yay. Maybe my view's just bad. Oh, yeah, we have people. Okay. Um, so I was on the ball this morning. So, boom, stuff. So, real quick, as you're writing this stuff down, um, brought this up yesterday, and I think only a handful of you heard it because, lab. Um, so, for the uh, corrections, what I did is I left a column with the grade that you got initially, and then I just added a new column that was the points you got from the correction. If you add those two columns up, that's what you got out of 100. And yeah, so that's how that worked out. So it looks a little funny in the grade book, but just add the two together, and that'll be your total for your exam. So yeah, so your next test will be well, not next week, the week after, the week before Thanksgiving. I'll try to get it done to give you like Sunday to Friday to do it, or Monday to Friday. I'll give you more time. Um, what else? We're gonna get through some part of these slides today, and then I'll probably make like another synthesis to kind of go through, maybe introduce a new reaction or two there, and then also just kind of reinforce stuff that we've gone over. And that should basically get us to the end of the semester. Fingers crossed. So yeah. So for this first thing, if you have a double bond, there's no other stereocenters around, no other functional groups, how can you turn that into a single enantiomer of an epoxide? So a sharpless requires that you have an allylic alcohol. So to do a sharpless, you have to have an alcohol because the titanium has to coordinate to the alcohol to be held close to the double bond. But we went over another one that works on like isolated double bonds, so that you don't need to have a what's it called, a another functional group around. It'd be a She epoxidation. So right, right, there's going to be a She catalyst, right, which is a sugar-based thing. And then make sure I can actually get the right reagents here. Right, you need where's it at? Some oxidant. I guess it's and butyl. Writing this right. NHSO4. And NAB 407, right? And then solvent. It's a really bad NH. Try again. NHSO4. More terrible things that really aren't letters, apparently. And not apparently, clearly. NAB407. Yeah, that looks like I wrote shirt. It should be she catalyst. There you go. So then the next one, how can we take it a little like alcohol and turn it into a single enantiomer of a cyclopropane? So the person's name is Charette. So it's the Charette modification. So what do I need to do that? So Charette cyclopropionation. It's a variant of a Simmons-Smith. So this Charette you use, they have, the example we have is zinc and like zinc bound to like iodomethanes or methylenes, right? And then it has a chiral ligand, which is that's really bad. Let me try again. Man, I just can't like draw anything today. There you go. Yeah, effectively. These are backwards from the example we have, but you get both enantiomers. Good job, me. Just to make it match the example that we have in the notes. There you go. It's a little ugly. All right. So you have to have a chiral ligand plus the stuff to do the Simmons-Smith cyclopropionation. So a zinc on with carbon and with a CH2 and an iodide, or diethyl zinc and diiodomethane. It's more complicated. I wouldn't worry about it. One sec, I gotta fix something real quick. Oh, okay, that's good to know. I thought I figured out a way to record another way, but I can't. Okay, cool. Yeah, so don't worry about if it's going to be wedge or dash, right? Just worry about that it would give you one enantiomer. And like I'm not going to go through like how you would pick which catalyst you need. I think that's just a layer too far for what we're doing. So So just don't stress too much about that. But there's more. I'm going to make this an OH. And I'll make that an actual element. There you go. Do you remember how this would work? What we get here? No. So first, I guess we got to remember what MCPBA does. Right. So MCPBA is something we learned organic 2. Right. And anything that is kind of a per acid, where you have a carboxyl group and then peroxy linkage O bonded to O, right? That's going to be able to make an epoxide, right? So MCPBA makes epoxides, right? And having the OH, right? If you remember, the OH will direct the epoxide to the same side as the alcohol, right? So we're going to make one diastereomer, and that diastereomer is going to have the oxygen the epoxide and the OH on the same side. All right, and that's because I'm going to go over a slide. I'll come back to this last one. But to kind of show why that happens, or to remind you why that happens, right, that you have a situation where you have this OH and this oxygen, there's a double bond, there's a hydrogen bond between the oxygen of the alcohol, there's a hydrogen bond between the hydrogen of the alcohol and the first oxygen, the oxygen that's bonded to the carbonyl carbon of the MCPBA. So now that's going to hold that whole reagent on the top side of the double bond. And then the second oxygen is the one that, well, then this hydrogen ends up over here. But all right, but this holds that oxygen to the top face. So then when the epoxidation occurs, it has to be on the same side because our oxygen's holding it on the same side. And then last thing is, right, first, What does that do? Absolutely. No problem. No worries. Sure. So diethyl zinc and iodomethane is what kind of reaction? What does that do? So what are we going to put on the double bond, or where the double bond was? Jonah said it earlier. That is a Simmons-Smith, exactly. So that's going to turn the um, double bond into a cyclopropane. Then, right, we have to know which side of the double bond we're approaching because, right, we have this allylic chiral carbon. Right, so that allylic chiral carbon is going to control how the reagent approaches the double bond. So I've done this in my head. We're gonna have to check and see if I'm right. Right, but it should be up. Right. And the way we do this is we draw that A13 minimized transition state, right? Where you have to take this. I'm going to go over. I'm going to redraw it and go over, or go over then redraw it, so we can work with it. Right, where you take this guy and you draw the A13 minimized structure, and that's going to put the hydrogen like inside. So if you have this drawn like this, now your hydrogen sticks inside, right? And then you're going to have a methyl group up and isopropyl group down, I do believe, right? So this is 1, 2, 3. This is R. So if I didn't mess this up, right, and it's a little hard to see, right, this is still going to be 1, 2, 3. And if you kind of turn it in your head, you can see that if you turn it, you can put the hydrogen back away from you. This should still be R. Right? So I've drawn the right chiral center. So from the top face, the reagent would go past a methyl group. Coming from the bottom, the reagent would go past an isopropyl. The isopropyl is bigger, blocks the bottom face, so reagent comes from the top, comes from the same side as the methyl group. So the last thing I wanted to do is I wanted to do one more type of cyclopropionation. And so one last cyclopropionation. It's like I totally lose the ability to like write and spell. I say lose, that implies that I had. Right. So the last one is, I'm going to do a really simple example first. So you have a diazo compound, which is the N2, if you can draw it right. And then you're able to treat this with ruthenium, right? Ruthenium, yes. No, rhodium. RuRH, they all just blend together. Rhodium acetate, I do believe. To be right. And then a double bond. And what happens is this rhodium reacts with the diazo compound and makes something like this, where you replace the nitrogen with the rhodium, and he's got some acetates on there still, right? But this is now a carbene, right? And we've talked that a carbene is a carbon that has a lone pair, but also has an empty orbital. So it's a carbon that can add to things and be added to. And this is able to react with the double bond and make a cyclopropane. So they can make these catalysts chiral. Oh, I didn't put down the actual ligands, that's all right. They can make these catalysts chiral by changing the acetates to chiral things. So the way these catalysts look is you've got let me look right here. So they have the 4 acetates kind of go around them. The other 2 are hard to draw, right? Because they're like kind of at a weird angle. They get really ugly really fast. Basically, you can think of it as almost like they call them like lanterns, where you have these 4 acetates around the outside, and then the part of the catalyst that reacts is here, right? This open spot on the metal at the end. So what they're able to do is if you go from an acetate to, if you put something chiral on these ligands, as opposed to having methyl, you have some chiral group, you can make your catalyst chiral. So the simplest thing is rhodium acetate, and it will cyclopropionate things. But as soon as you put a chiral ligand on the metal, then you can do it asymmetrically. This stuff, this chemistry is really good, but it is limited to, depending on what paper you read, they're called push-pull carbenes or diazo compounds. So So what you need some electron withdrawing group, something that can pull electrons away from the carbene you're going to make. That's the pull or the acceptor part of it, right? That can accept electrons. And then you need something to have to donate via resonance, right? So that is the push or the donor. You need something that can like give electrons to the carbene that you're going to make. So you're kind of limited. The most common version of these is you have an ester or an amide on one side and you have an aromatic ring on the other, right? You need that to make the carbene that you generate, to make the structure where you replace the nitrogen with the rhodium stable, so they just don't fall apart right away. So you are a little limited, but these do a whole lot of chemistry, and they have been used really, really, really successfully to introduce chiral centers, to like make a molecule that can be turned a lot of times in like 7-membered rings. So they're pretty useful, but they are limited to, you're always going to kind of have an aromatic ring and an ester in your product. So I picked 2 examples from the Davis group from Emory, because he's the one who has done this the most. And I picked 2 slightly different examples. So here you see that classic donor acceptor diazo compound where you have the ester in the aromatic ring. I'm not going to get too tied up in, or have you get too tied up in what the actual ligands are. Suffice it to say, like, this is something that is a carboxylic acid or a carboxylate that then has a big chiral group sticking off of it. I think this one has like the biggest possible group you can have on it to differentiate the 2 sides, right? But they're able to cyclopropionate one of the double bonds of a furan. So furans are aromatic, but they're not nearly as aromatic as benzenes, right? So benzenes are way less reactive, but still it's aromatic. But this is good. This reagent is good enough that it can cyclopropionate one of those double bonds selectively. And I guess they saponify this. That I don't remember. I might have just messed up, but whatever. All right. And then in another paper, they wanted to try to get away from having the ester, so they're able to introduce like other aromatic groups, like electron-rich or electron-poor aromatic groups, to get that same donor acceptor like structure, but without being stuck with always having an ester. And they're able to cyclopropionate styrene in good EE. So something you want to notice, you want to look for in reactions sometimes that you might not think to look for, is here they use 10 equivalents of styrene. So they have to use a really large excess of styrene to get this reaction to work. So that really kind of limits the synthetic utility of this reaction, because let's say you wanted to do this reaction, right? But you weren't working with styrene. You're working with something that was more valuable, right? Something that you spent 3 months or 6 months making. You couldn't just use 10 equivalents of that like valuable starting material, right? You have to like wait. You will not wait. You have to, right? You wouldn't want to throw away a bunch of reagent because you couldn't use it right? So these kind of things where they're like, hey, here's this super cheap thing, and we used a big excess of it. Like, it's great that the reaction works, but it does limit, like, you're not going to want to use that in the, like, as the, in the 10th step of your reaction, of your synthesis, because you can't just, like, throw away that much material, right? So this works really well when you're using something cheap and easy, but if this double bond was something that took a long time to make, you wouldn't want to use a large excess of it. When you could try to fish it back out of your reaction, but it just ends up being a lot of extra work. So sometimes there'll be neat reactions that you're like, oh, that's something I'd want to use. But then you see that it's like, oh, it only works if they use the one reagent as the solvent. And you're like, oh, well, I can't use my stuff as a solvent. It's a solid, or it's something I spent months making. I can't just like lose a bunch of it. But these ones here with the esters, these work great. These work in syntheses all the time. So it's, and these are all catalytic in rhodium. So you just need a little bit of this. It's like usually less than 1 mole%. So I think this is like the end of additions to alkenes, right? So, right, there's a lot of ways that you can get stereochemistry when you have alkenes. There's allylic control, so using existing stereocenters. There's coordination, where you're coordinating to a group. Again, this is another example where you're using an existing stereocenter to that's already in your molecule to set the next stereocenter that you're going to make. And then there are chiral reagents or catalysts where you have where you've taken something that's chiral and you've attached it to a metal, or you've taken something that's chiral and you've made it so it can do a reaction, and then you've used that. And so you can take a starting material that has no chiral centers and then install chiral centers by using a chiral reagent or catalyst. So getting your chirality from outside your molecule and transferring that to your molecule. Now, clearly, this is not like an exhaustive list of all of your possible ways that you can install chiral centers. This is just kind of a sampling, if you will, to like let you know what's out there and to give you a sense of like, oh, maybe if I need to install a chiral center, you know, maybe one of these reactions doesn't work, right? But let me look on SciFinder or look in the literature and see if there's an example that does work, because this is a chiral that people have been working on for a really long time, and there's a lot of different reactions out there to install chiral centers in different kinds of molecules, right? If you need to make an aziridine, which is the nitrogen version of an epoxide, right? You replace the oxygen of an epoxide with a nitrogen, right? There's a bunch of ways to do that. There's a bunch of different ways to do hydrogenations. There's a bunch of different ways to do cyclopropionation. So there's a lot of different ways to do these reactions, and almost every reaction that you can think of, there's usually some sort of asymmetric variant or some variation where you can install a chiral center this way. So I wanted to like show you how some stuff works, but also just let you know that like this is the basis, and so the reaction that you might need, you can go find and see if it actually has an asymmetric version. And the answer is usually going to be yes. So that is the end of alkene reactions. Get rid of this. So the next thing I had was, if I have, let's use it fun here. You know what? We're just going to live with that. So I think, I could be wrong, I think when I made my slides, I meant to write, how does all this work? But I wrote, who does all this work? And that's also a good question. Who does all this work? The answer is grad students. Okay. So I want to talk about carbonyl additions and how you can use chiral centers that are already in your molecule to convey chirality to the alcohol that you make when you add to a carbonyl carbon. So, right, the kind of the baseline reaction that we're trying to do, we're trying to illustrate, right, is, right, you have a carbonyl compound. I'll actually start off here. Right, so you have a carbonyl compound, you add a nucleophile, and you install. You make a new carbon nucleophile bond, and you turn your C double bond O into an OH. Right? We can do this with aldehydes, make secondary alcohols. We can do this with ketones. And make tertiary alcohols. So we saw this in like Organic 2 with like kind of the classic way of doing this was, right, you took an aldehyde, you added an organometallic, usually a Grignard reagent. And you make an alcohol, right? So if you remember, right, Grignard, the metal is plus, the carbon is minus, that carbon adds to the oxygen, pushes electrons up. You get your alkoxide, your O minus, right? That's got your O minus. It's got your magnesium bromide hanging out nearby, right? Making a salt. You don't want the salt, so you add acid after you've added all your Grignard. So after all your Grignard's been used up, you add your acid. You protonate your oxygen, you make your alcohol, right? So what we're going to focus on is what happens if your carbonyl group, if there's a chiral center already in your molecule. How does that then get transferred? How does that influence how the nucleophile adds to the carbonyl carbon to make the to make a new chiral center? So right, so you've got your aldehyde and you have a chiral center right here. Right, when you add your Grignard reagent, right, you can make two products. You can put your OH back and have your Grignard reagent added. Plus, you can get OH forward. Right, so you can make two possible diastereomers. And the point of this is figuring out how we can get which of these diastereomers we're going to get the most of, which one we should expect to get from our reaction, right? Okay, so which of these we're going to make, and that's what we're going to talk about, is how you predict which of these compounds you're going to make, okay? Or which ones you should expect to make. So, all right, we're going to look at a few different models that have been used to predict which of these you're going to make. Okay, there's the Cram model, there's the Cornforth model, and then there's the Falcon-On model. And the Falcon-On model kind of takes the best parts of the Cram and the Cornforth model and puts them together as kind of like a grand unified theory of how this works. But there are some interesting things that you can take from the Cram and the Cornforth. Right, so it's kind of similar to like the A13 allylic induction stuff, where you have to model your molecule in its like most stable conformation and then see what sides are available. Okay. So the Cram model, you kind of have your chiral center, right? And you can think of these as like drawing Newman projections, right? Where you draw a Newman projection of your aldehyde or ketone, where you look down the aldehyde, right? Where you look right down the bond that goes from the aldehyde or the ketone to the chiral center. Right. So the Cram model sticks the large group basically eclipsing the group on your carbonyl, which explains the selectivity, but isn't wholly satisfying, right? Because like eclipsing things are bad. So I'll let you guys draw this, and then I'm going to go over real quick kind of how this got drawn. I'll actually draw it out, and then we can check and make sure that like the chiral centers are right and kind of see how you can do that. Make sure you don't switch your chiral centers when you do these. I'll give everyone a sec. So I'm going to switch over to the whiteboard if that's okay. If I can find how to switch to the whiteboard. There we go. Okay, so right, if we look at what we had, right, you've got your small group back, you got your medium group, and then you have your large group. Right, so the way it's drawn right here, right, you can see that your whatever your R is eclipsed with your large group, right? They're lined up with each other. If there were no carbonyl, right, it would look something like that, where you'd be like, oh, hey, this methyl group and this methyl group are in the same plane, they're eclipsed. right? So what you're doing is you're drawing this carbon right here is your front carbon. So you're looking, again, crappy Wakefield eyeball, right? You're looking down that carbon, so through the carbonyl carbon back to the chiral carbon. So that's how they have it drawn, where you have this, where your R group, that's this carbon right here. And then I'm going to make this a little longer. Right, there you go. And then you can kind of see, like if you were to take this and turn it, right, or if you're looking there, that your small group is here, your medium group is here, and your large group is here. But what you can do to kind of check, right, is you could say, okay, let me say that we go carbonyl is 1, 2, 3, right? This looks R, right? There's an R chiral center, assuming that, right, the carbonyl is highest priority, then the large group, then the medium group, right? Within the small group being 4, right? We can check that here. We can say, okay, 1 is the carbonyl, 2 is the large group, 3 is the medium, and 4 is this. And now here is where you kind of have to like do the mental Tetris. It's a lot harder to not do it, right? But if you thought about taking this structure and like turning it, right? So imagine if you turn this so that you had your 1 over here, your 2 right here, 3, and then 4 is straight back, right? That's basically what you do. So you kind of like take this to get from here to here. You kind of take this carbon that's like in plane and you pull it over. So you just kind of turn it at using carbon 2. So you just kind of like grab the large group and you kind of twist so that your 1 is no longer sticking straight at you. Your 4 is then sticking straight back. I don't have a model to do this. I'll bring a model on Tuesday. All right, so now you have your 4 back and you have 1, 2, 3, and this is still R, right? So I've drawn the right chiral center because I can check it in my Newman projection. All right, so you just have to kind of like see that your small group is in plane right now, and you have to turn it so it points. I guess it would point away from you, right? So you have to turn that and see how everything turns when you twist that away. So you can check on your Newman projection. Now, what this model does show, and it's something that's going to come up a lot, is that the way your nucleophile adds for all of these, regardless of the model that we're using, is the same, right? You add kind of at an angle to the carbonyl carbon. So your nucleophile always comes in kind of, oops, I can draw it, kind of at an angle. And I'll talk about what this angle is called. Can I find it real quick? I'm going to jump ahead. Maybe I'll spell it here. This is the Bürgi-Dunant angle. So it comes in always at this kind of same angle, because what it has to do, your nucleophile has to get to an orbital, right? And the way it gets to that orbital is it follows this trajectory to add to the carbonyl carbon, and it always follows the same trajectory, because on your carbonyl, there is, okay, that looks really bad, but just bear with me. Don't get me fired. That's really bad, right? These are I drew it and I was like, this is awful, right? So these are the pi star orbitals. These are the orbitals that if you add electrons to them, they will break the bond. So you have to have your nucleophile put its electrons into the pi star orbital, because adding your electrons to this orbital breaks. So adding electrons breaks the C double bond O. It breaks that carbon-oxygen double bond, right? And that's what I'm doing when I add to a carbonyl carbon, right? I make a new bond, but I have to break the carbon-oxygen double bond. And I do that by adding to the pi star orbital. So that pi star orbital is always along this Bürgi-Dundas angle. So your nucleophile always adds to that, approaches along the angle that gets it directly to that orbital. Sorry, had to make sure my headphone was paired before I switch the other one out. Okay. So this is the CRAM model, and this is kind of the basic where we started our understanding of how we add to carbonyls that have alpha chiral centers. Right. The next thing is the CRAM chelate model. And this is something that like we still use and it works really, really well. Really well. Right. What you do is this is what happens when your alpha chiral center has a group that has lone pairs on it, right? That has this G group here that can be usually an oxygen or a nitrogen, right? So an ether or an amine. And what this does is if you add the right kind of metal, you will make a ring. And then you're not dealing with an acyclic structure, you're dealing with adding to a ring. So I'll let you write for a second, and then I'll switch over and I will write some stuff myself. All right. So I'll come back in a sec if you need me to come back. Fine thing to share. All right. So basically what you're doing is you're turning acyclic structures into rings. To metals. Right? So you take this acyclic structure, you add a metal to it, and it makes it act like a ring. And this is important. Being a ring, makes it so they're rigid, right? Rings are rigid. There's definite faces to a ring, right? Your single bonds aren't able to freely rotate, right? When you have an acyclic structure, right? So we'll just pick like a simple acyclic structure like butane, right? I'm able to rotate all the way around this single bond, right? I can get all the way around and I can get back to where I started, right? So acyclic structures rotate, right? The single bonds are free to rotate all the way around. There's nothing stopping them. When you have a ring, I can't rotate around this bond, right? I can't rotate around that bond. I can't do it, right? Because it's a ring. If I try to turn all the way around that bond, right, I have to break my ring. So if I can turn an acyclic structure that's kind of floppy and is free to rotate in any given direction into a ring, I know I have a lot more sense of what the structure looks like and how things can approach. So what happens is you have a structure, right? You've got something that's like this, right? And if this is just an acyclic structure, right, I can rotate around this bond. I can get to a conformation that looks like this, where I have something like this, where it's like, okay, well, which side do I want to approach from? Right, I want to, you want to add to the carbonyl from the side opposite the tert-butyl group, right? Because the tert-butyl group's the big group. It's the hard group for you to get past, right? But which conformation is your molecule going to be in? Is it going to have the methoxy group up, as I have it drawn here, right? Pointing on the top side, or is it going to be on the bottom side, right? When you can rotate around that single bond, there's a lot more uncertainty as to which conformation you're going to be in. But when you add a metal, right, what happens is that metal gets bound between the oxygen of the carbonyl and the oxygen of this ether. Right? Now, the only way that I can make this five-membered ring is if I have my oxygen on the top face. Right? My oxygen has to be pointing up. Right? So now I know exactly what conformation my molecule is going to be in, right? I know I've made a ring. I have a ring now, and I know which face is the open face and which face is the blocked face, right? So the front face, the face with the tert-butyl group, is blocked because you've got that big group. The back face with the methyl group is the open face. All right, so when your nucleophile adds, you're going to add your nucleophile. Is going to approach from the back face, right? It's going to come from the side of the methyl group. And what that does is that puts the oxygen forward, the nucleophile back. So your nucleophile is going to end up on the opposite side of your large group. And then you have your H. So because you make this ring, you've now fixed how you're going to, how your molecule is going to behave. You've taken all the rotation out of the single bond between the chiral center and the carbonyl group. And so you've locked the molecule into a structure where it's going to only have one conformation. And then you can predict based on that one conformation where your nucleophile is going to add from. Right? So the metal is important, right? So in our little drawing, the G group, right, is going to be, again, ethers or amines, right? Normally is going to be like a tertiary amine, right? The metal, right, is going to be something small and densely charged like lithium. Now, you're going to yell at me. Hydrogen is not a metal, but it is positively charged, right? I need something that has a positive charge to hold together that G, right? That oxygen or that nitrogen that has that lone pair, and then the lone pair on the carbonyl oxygen, right? So I can put a hydrogen here, and these electrons on the G are going to make a hydrogen bond to it, and the lone pairs on the carbonyl oxygen are going to make a hydrogen bond. Right? These aren't full bonds, they're just association. So I'm not breaking any rules where like hydrogen is making two bonds. It's more something where this lone pair is attracted to this hydrogen, and this lone pair here is attracted to this hydrogen. And so they kind of just hang out and hold on to it, but they're not making full-on bonds. Right? Or it can be something where the metal has, so these are the small charged ones. Small, densely charged, I should say. Right? Or it can be metals that just naturally have the ability to make multiple bonds. So then you can have things like magnesium, titanium, tin, and aluminum. These all kind of naturally make um, multiple bonds, right? So these have multiple coordination sites where they are able to bind to more than one thing, right? So they're almost even better than like lithium, because they have coordination sites that are available to bond to. So these ones up here in blue, right? These more rely on like electrostatics, like, hey, I'm positive. You have some electrons that are negative. We're going to hang out close to each other, right? These ones that are in orange, they actually have open sites, open orbitals that you can put electrons into, right? So these ones work a little bit better, but they're all doing the same thing. They're all making this little ring. So things that don't work are things that don't have empty orbitals or aren't densely charged. So the M to do a cram chelate can't be a boron. Right? Boron is only able to bond to one lone pair at a time. right? To make this chelate, you have to be able to bond to 2 lone pairs at the same time. Boron has that one empty orbital that we use all the time, but it doesn't have a way to then interact with a second lone pair. And then you have ammonium. So ammoniums don't have an empty orbital, right? The nitrogen's positive because it's making too many bonds. The last thing it wants to do is make more bonds, right? So it doesn't have any orbitals to like have lone pairs interact with. So the only thing it can do is try to do that electrostatic thing where it's like, hey, I'm really positive, have your electrons hang out with me. But the ammonium's way bigger. And so it's kind of a squishy positive charge. It's not this small, really dense thing that your electrons are going to be strongly attracted to. It's this bigger, more diffuse positive charge that doesn't get that same like strong interaction. So if you are using boron or ammonium in your reaction for some reason, you're not going to do a CRAM chelate model. You're going to use some other model to predict how you're going to get your stereochemistry. I think the CRAM chelate model is kind of the easiest to see just because you make these little rings and like it works really well. So I could go on for another 8 minutes, but we'll stop here. We've gotten through the CRAM stuff. We'll do Cornforth and Falcon on Tuesday, and I have some examples, and we'll do Aldol stuff. We'll see where we get. But I think that's good. So I have you all here real quick. So my plan is for lab is that next week we'll finish stuff up. We'll try to isolate our alkene. And then the week when you like probably the week the if I could talk, I had it all planned out in my head, then I like lost ability to word. Um the week before Thanksgiving, maybe when you send me your second exam, just we'll basically get like your notebooks, and I'm just gonna go through your notebooks for lab and make sure that they look like you actually like took notes and stuff and wrote up stuff and did all the math, and that'll be your grade for lab. So I'm thinking that, like I said, the Friday before Thanksgiving, just when you send me your test, just send me your lab book as well. And I'll send out an email to remind you. But that way I can just like look over everything over break and I can get your lab grades done. Because I think your lab grade is like you all showed up and you all did stuff and you kept a lab notebook. For a lab that just got thrust upon you that was 100% different than what you were expecting, I can't ask for much more than that. So just have it in your head that you need to have your lab notebook kind of together and, you know, somehow gotten to me uh, the week before Thanksgiving, and then I'll look over it. So with that, if there aren't any questions, like I said, we'll finish off some of these models. We'll do some examples on of these on Tuesday as well, and then we'll go from there. So with that.